Hello, my name is Tyler Hayes and I am a current PhD student at the Rochester Institute of Technology. Today I am pleased to present our work, Lifelong Machine Learning with Deep Streaming Linear Discriminant Analysis. A preprint of our full paper is available on arXiv and our code is available on GitHub. Links to both of these materials are provided at the bottom of this slide. Although humans are able to continuously acquire new information throughout their lifetimes, deep neural networks struggle with this problem. When trained on non-stationary data distributions, deep neural networks catastrophically forget previous knowledge. Moreover, neural networks are unable to learn new information immediately. In lifelong learning, we require agents to overcome these challenges while also being subject to severe memory and time constraints. Within the field of lifelong learning, there are two popular paradigms in which agents are trained. The first is incremental batch learning, in which a dataset is broken into several batches, where each batch often consists of several classes. At each time step, an agent receives a batch of data and is allowed to loop over this batch until it has been learned. To accurately capture the agent's performance, it must be evaluated at the end of learning a batch. Although this paradigm has recently demonstrated much success, it comes with caveats. Waiting for a batch of data to accumulate before training an agent and looping over a batch several times can both be restrictive in real-time learning scenarios where agents must learn and make decisions immediately. In contrast, online streaming learning is closer to how humans and animals learn. In streaming learning, an agent receives training instances one at a time and is only allowed a single epoch through the dataset. Since training samples are provided one at a time, the agent can be evaluated at any time, making this paradigm more amenable to real-time learning. In this paper, we propose the Deep Streaming Linear Discriminant Analysis Model, or Deep SLDA. Deep SLDA is a simple baseline that consists of a pre-trained deep CNN backbone, a running mean vector per class, and a single shared covariance matrix. During training, an image is first passed through the CNN backbone to extract an image feature. Then, the associated class mean vector and tied covariance matrix are updated using running estimates. During inference, predictions are made by assigning inputs the label of the closest Gaussian in feature space defined by the class means and covariance matrix. We evaluate Deep SLD's performance on two datasets. The ImageNet 2012 dataset has been commonly used to assess the performance of incremental learners. It consists of 1,000 image categories with roughly 1.28 million images. Since streaming learners can be impacted by the order in which data are presented, we also use the CORe50 streaming dataset consisting of videos of a person moving different objects around with their hand. CORe50 consists of 10 classes and 6,000 images. We compare SLDA against several incremental batch and streaming baselines in the single-headed evaluation paradigm, where task labels are withheld from the models. We compare two variants of SLDA, one where the covariance matrix is held fixed after initialization, and one where it is updated incrementally. We compare both of these variants against the extreme model that combines streaming clustering with replay. We also assess the performance of ICARL and end-to-end incremental learning, which are two popular incremental batch baselines that combine replay with a distillation loss. Lastly, we compute the performance of an offline model trained from scratch to determine the upper bound on model performance. Here, we present our results on ImageNet. We first allowed all models to initialize their features offline on 100 classes of ImageNet. The streaming models then learned the remaining classes one example at a time, while incremental batch learning models learned batches of 100 classes at a time via looping. A learning curve is depicted on the right and shows that SLDA achieves the best final top 5 accuracy while outperforming ICARL and Extreme at nearly every increment. Moreover, our SLDA approach requires only 30 minutes to train and evaluate on classes 100 through 1000 and requires only 0.001 gigabytes of memory beyond the CNN. This is remarkable as methods like ICARL and end-to-end require nearly 62 hours to train and over 3 gigabytes of storage for the replay data. Next, we ran a series of experiments on the CORe50 dataset. Since CORe50 is much smaller than ImageNet, we first initialized the CNNs with ImageNet weights and then fine-tuned them on a small subset of CORe50. Since several models require task labels to be provided at test time, we ran two versions of our experiment, one where task labels were provided and one where they were not. We evaluated performance on CORe50 after every 2 classes were learned. This means that when task labels were provided, the problem reduced to binary classification at each increment. The performance of each model with respect to an offline baseline is on the right side of the slide. We found that multi-headed regularization methods performed poorly when task labels were withheld during inference, but SLDA outperformed all baselines in both scenarios. In conclusion, we propose Deep SLDA as a simple baseline that achieves remarkable performance, while being more computationally and memory efficient than existing approaches. Deep SLDA combines a pre-trained deep CNN with independent running means and a shared covariance matrix that allow it to remain robust to forgetting. SLDA can be thought of as a way to train the output layer of a neural network. While representation learning may improve incremental learning performance further, we urge developers of future incremental learning algorithms to test simply training the output layer to ensure that representation learning gains are actually being realized. Lastly, thanks to our sponsors for funding this research.